Hello also from my side. I'm Verena Kerschenbauer, as Robert said, and I'll briefly present our results of our economic calculations. Before we look at the results, I would like to give you a short introduction. As part of the economic feasibility analysis, we developed and examined 4 CO2-based scenarios. And in addition to that, we defined 4 comparison scenarios based on water the heat transfer medium to enable a clear economic assessment. Now I will only focus on 2 selected CO2 scenarios, and these 2 are the most promising ones in our opinion. First we have the case CO2 only cooling. In this scenario, the simulated network provides cooling only, so the required heating at the consumer must therefore be supplied by conventional systems. And the second CO2 grid we want to look at is the CO2 heating and cooling. Here we consider a CO2-based network in which a lake serves as a source of both for heating and cooling. And this effectively provides a free heat source because we have the lake. And the key advantage is that the network can supply heating and cooling at the same time in the network, not at the consumer, but in the network, as I think Robert said before. In addition to that, we have the 4 comparison scenarios which we have defined. We have the ref only cooling, which represents the reference scenario for case only cooling, so we can only cool in this scenario, and the heating has to be provided from another source. Then we have the REF 5G-DHG, which describes a modern 5th generation district heating and cooling network. We have the REF conventional, which represents a typical biomass-based district heating network, and which is, I think, very common in Austria. And we also have the district cooling network, which is operated by a chiller. The REF conventional heat pump is essentially the same as the previous scenario, but here the heat pump is used instead of biomass. This represents a district heating operation which is commonly found in Denmark. For the economic feasibility analysis, we have made some assumptions, and the most important for now are the electricity price we assumed. Here we assumed a constant price of 20 cents per kilowatt hour. And another very interesting price is the district heating price, with which we sell the heat. And there we assumed for low temperature systems, so for all CO2 systems, and the REF 5 GHG, and a price of 8 cents per kilowatt hour, and for the networks with a higher temperature, we assumed 12 cents per kilowatt hour. Only to mention it, we also have factored the service of life of the materials according to the EFA. When we now look at the calculated investment costs for each of the networks, it's clear that the largest portion is attributable to the heat pump or the chiller. And another significant portion, the pink one, are the pipes. What you can see here in the first view is that in the 2 conventional systems, we have nearly twice of the cost for the pipes, and the reason for that is that we have this 4-pipe system, so we need an own system for the district heating grid and an own pipe system for the district cooling grid. Overall, when we only look at the investment costs, the highest investment costs can be noted in the 2 conventional scenarios. Then let's take a brief look at the operating costs, which we calculated. And here we can see that in the CO2 scenarios, the main costs naturally arise from the purchase of electricity. In the 5th generation scenario, we also associated and purchasing heat, which we buy from an existing district heating network. That was an assumption in our calculations. And yeah, all in all, I think what can be seen is that the CO2 network incurs an operating cost of around 700 to 800,000 euros. And for the conventional network with the biomass, so REF conventional, and the 5th generation network, we have in every case to buy an energy source and heat source. We have much higher operating costs by about 1 to 1.2 million euros. Yeah, now we have seen the investment costs and the operative costs, and that allows us to examine the cumulative cash flow for each scenario. If we first compare the CO2 only cooling with the REF only cooling, and the cumulative cash flow over the CO2 based network is slightly better than the one of the conventional network. However, a closer look shows that this difference is mainly due to high investment costs in the conventional system, which we can see by year 0, where we have about 1 to 2 million euros more in the investment costs. Overall, and the large costs are very expensive heat exchanger, what's the reason for the investment costs? And this, at the same time, both systems are roughly equally profitable during operation, because they're nearly parallel, as we can see. And so the main difference are the investment costs, which make it that the REF only cooling, so the water-based system, isn't as profitable than the CO2 grid. Yeah, when we now compare the second CO2 case, so the CO2 heating and cooling with the reference scenarios, we can see that there in yellow we have the CO2 grid. In red, there is the REF GTHG. In purple, the REF conventional, and in green, the REF conventional heat pump. And looking at the long-term trend, it becomes clear that the REF conventional heat pump scenario, where we use a heat pump for the heat supply, cannot economically compete with the CO2 scenario, and also not with the other two reference scenarios. Yeah, and the situation is different in the classic conventional scenario, thanks to comparatively low operating costs and stable revenues. It can catch up with both, so the modern 5th generation grid and also the CO2 grid, after about 30 to 40 years. And in long term, so after the 20 years of operation time, which we assumed, we have nearly the same results in profitability in the conventional system than in the CO2 networks. Yeah, to ensure a fair comparison, it's important that, as I said before, we have been working with fixed price so far. So for electricity, we assumed the 20 cents per kilowatt hour. And so in the next step, I will show you the influence of the electricity price on the results. Yeah, and on the left side, we have the case that we have a rise in electricity price, so a 2% rise in electricity price. And this would primarily benefit the REF 5GTHG scenario, which would then achieve the highest cumulative cash flow in long term. So you can see the red line has the highest cash flow. On the other side, we have the annual drop of 2% electricity prices. And here you can see that the case heating CO2 heating and cooling, and also the conventional scenario has the highest profitability. So we have nearly the same results than when we don't change the electricity prices. What also can be said to this slide is that summary the case heating and cooling, so the CO2 case, is highly depending on electricity price, which we also see in the slides, because when we have this increase in electricity price, it's nearly worse than the conventional and the 5G DHG. And when we have this drop, it's nearly the best. Yeah. So to zoom up with the results of the economic calculations, there are two main results. First are the CO2-based system are expected to be economically competitive even at this early stage of development. So for heating and cooling, similar results to those of a conventional biomass-based heating and separate cooling network are reached. And for pool cooling scenario, we have slightly better results than they are expected. And the second main result is that external factors like electricity price have a big impact, which we have before, but what's important to say here that this impact can be used strategically, even if we think about flexible tariffs or anything else. Yeah. Thanks for your attention.